Okay guys, let's review. We're going to look at the review for our logarithms test. So the first page that I'm doing the review does require a TI calculator. So these are things you've seen before in our studies of logarithms. The 2010 Haiti earthquake measured 7.0 on the Richter scale. The 1994 earthquake was 5.4. How much stronger was the 2010 quake? We have a formula for earthquakes. The magnitude is equal to the log base 10 of the intensity. So they're asking me about the intensity of the earthquake. So in this case, I know that the way we worked all of these problems, 7.0 minus 5.4 is equal to 1.6. Okay, so if I look at it, 1.6 is going to equal to the log base 10 of the intensity. Okay, this is a log equation with a log on one side. I solve this by converting to exponential. So remember, that's my exponent in a log equation. So 10 to the 1.6 equal I. That's something I will use my calculator for. So 10 raised to the 1.6 is 39.81. So I know that 39.81. So that tells me that the 7.0 quake is 39.81 times stronger. So it's almost 40 times stronger, the 7.0 earthquake, than the 5.4. All of these problems will work just like this. You'll have this formula, and you'll be given two numbers for the earthquake. Find the difference. When you find that number, that's going to be on the other side of the equal sign all by itself. That's your exponent. And then you convert to exponential form, use your calculator, and then answer the word problem with numbers and words. Solving an exponential equation using your calculator. What we want in this particular case is I want to be able to take the log of both sides. So really what I want first is I want to get an exponential on one side all by itself and then take the appropriate logarithm. So in this first one, if I divide by 5 on both sides of the equation, I get e to the x plus 4 equal 12/5. The base here is e, so I want to take the natural log of both sides. So I'm going to take the natural log of e to the x plus 4 equal the natural log of 12/5. The reason I take the natural log is because the natural log of e to the x plus 4, that is just x plus 4. So x plus 4 equal the natural log of 12/5. So x is equal to -4 plus natural log of 12/5. Okay, so that's the exact answer on your calculator. You can get an approximation for that. So I can figure out that is -4 plus the natural log and of 12/5. And so get an approximation of that is -3.12. So that's about -3.12. Okay, I think I'm okay in this one. If you do all of the work and just leave your answer, you know, this is the exact answer, that's the approximate answer. So you can do that either way. Let's look at this one. Solving this particular equation, I want to isolate this exponent. So if I divide everything by 2, I get 3 to the x minus 6 equal 52 over 2 is 26. Okay. Now, I want to take the log base 3 of both sides because I see my base is 3. So the log base 3 of 3 to the x minus 6 equal the log base 3 of 26. The reason I take the log base 3, because the log base 3 of 3 to the x minus 6, that's just x minus 6. So x minus 6 equal the log base 3 of 26. So x equals 6 plus log base 3 of 26. That's the exact answer. And you need to be able to work through that to get to that exact answer. And if I want to approximate that on my calculator, 6 plus log 3 of 26. So 6 plus log base 3 of 26. 6 plus log 3 of 26 is 8.965. So that's 8.965. So that's my approximate answer. The next one, 7 to the negative 3x equal 20. I will take the log base 7 of both sides. The reason I take the log base 7 is on the left. Log base 7 of 7 to the negative 3x is just negative 3x. So to solve this for x, x is equal to the log base 7 of 20 over 3, and there's a negative in front of all of that. That's my exact answer, and if you're approximating that, negative log 720 over 3, so that would be negative log base 7 of 20 divided by 3, control, enter, negative 0.5131. So negative 0.5131. You need to be able to algebraically do what I did here to get the exact answer, and I will tell you in class whether or not I need the approximate. I think I'm okay if you get the exact answer. That's doing the harder work. It's not. I don't think it's required to go ahead and do that on the calculator. Let's look at this one. 2 to the negative 4x plus 1 equals 71. I want that exponent, the exponential part by itself. So 2 to the minus 4x equals 71 minus 1. So 2 to the minus 4x equals 70. In order to solve this, I will take the log base 2 of both sides of this equation. The reason I take the log base 2 is the left side simplifies. Negative 4x equal the log base 2 of 70. To solve that for x, I simply divide everything by negative 4. So x equal negative log base 2 of 70 over 4. That's the exact answer for that. So in all of these, your goal is isolate the term that has the exponential. Look at your base. So in this case, the base was, in this case, the base was e. Base was 3. Base was 7. Base was 2. And then I take the log that base. So you see in the first one, log base e, log base 3, log base 7, log base 2. That allows us to simplify one side of the equation and solve for the exponent. Now we'll move on to page 2 of this review. We are not using the TI calculator for this page. It says convert the following exponential equations to logarithmic equations. So just converting back and forth between logs and exponents. So if I look at this, the base is 5. The base is 5. The exponent is x. So in logarithm, this means that the log base 5 exponent always on the other side of that equal sign by itself. So, and then the only thing I haven't written is z. So the log base 5 of z equal x. The next one here, converting this. Here my base is e. My exponent is 2x. So I'm going to have log base e of 4y equal 2x. Another way to write that is ln of 4y equal 2x. Either of those is a correct expression. The next one here, 12 to the x over 2 equal 4y. In this case, my base is 12. My exponent is x over 2. In a logarithm equation, so I'll have log base 12. My exponent is always on the other side of the equal sign by itself. And then here's the 4y. Log base 12 of 4y equal x over 2. This next one here, my base is 2. My exponent is 5. So the log base 2, my exponent in a log equation is always on the other side of the equal sign. The only thing I haven't written here is the xy. Log base 2 of xy equal 5. Evaluating logarithms. Log base e of e to the 12, so a natural log of e to the 12. I don't know what this is. Let's call it x. Now if we convert this to exponential, now remember, natural log just means log base e of e to the 12th. Okay, so my base is e, my exponent is x. So if e to the x equal e to the 12th, then x has to equal 12. Okay. Another way of figuring this out is, remember, the log and the exponential are inverse functions. So the log base e of e to the 12th, that's 12. So your answer is 12, either way you look at it in this case. The log of 100, okay, this equals x. Remember, this is log base 10 if it's not written. So log base 10 of 100 equals x. Convert the exponential, that means 10 to the x equal 100. The only power of 10 that gives you 100 is 10 squared. So x equal 2 in this case. Log base 3 of 81. Okay, that means that 3 to some power equal 81. That's 3 to the 4th. So x is equal to 4 in this case. Now the next one says, take a logarithm and convert it to exponential, but do not solve it. So in this case, my base is 4. My exponent in a log equation is on the other side of the equal sign all by itself. So this means that 4 to the 9th equals 5x. Okay. In this case, remember natural log, that's log base e of x equals 17. So in this case, the base is e. The exponent is 17. This means that e to the 17th equal x. Next, we're going to simplify some logarithm expressions. Okay, so we want to simplify and have no exponents left over. So this is using our product, our quotient, and our power rule. So remember, I can write this as the log of x to the 4th plus the log of y to the 5th minus the log of z squared. And to get rid of these exponents, I'm just going to use the power rule. This is 4 log x plus 5 log y minus 2 log z. Next one, log base 2 of xy cubed. According to our product rule, this is the log base 2 of x plus the log base 2 of y cubed. To get rid of exponents, this is going to be the log base 2 of x plus 3 times the log base 2 of y. So again, I use the product rule and the power rule. In the last one here, we can write this as the log base 7 of x to the 1/3 power. That's what the cube root of x means, x to the 1/3. Now, to simplify this with no exponents, I'm just going to use my power rule. That's 1/3 log base 7 of x. Okay, continue on. I think we have one more page. Condensing log expressions as the log of one term. Okay, so this is sort of going backwards from what we just did. So I can write this as this is the log of x squared minus the log of y cubed plus the log of z to the 4th. So that means now I can combine with the product and the quotient rule. This is going to be the log of x squared times z to the 4th divided by y cubed. So I use my product and my quotient rule to put this one back together. In this case right here, I'm going to have the log of x squared y squared minus the log of z cubed. So this is the log of x squared y squared over z cubed. Another way of writing that, this was a fine answer, but the other thing you could have written is the log of x to the 4th y squared over z cubed. That is, you could distribute that exponent out. So either of these would be a good answer. Solving log equations. Okay, so in this case there are two varieties, one log on both sides or logs on both sides. In this one, I can get the log of one side by using my quotient rule. So this is the log of 6 over 3x equal 2. Okay, and remember, this is log base 10. It's common logarithm. So this, if I convert it to exponent, this means that 10 to the 2nd power equals 6 over 3x. So that means that 100 equals 6 over 6 divided by 3x. If I multiply both sides of this equation by 3x, I get 300x equals 6. So x is equal to 6 over 300, or what is that, 3 over 150. You're okay with wherever any of these numbers, or 1 over 50. Any of these numbers would be correct. Let's look at the next one. Now here I've got logs on both sides of the equation. So my strategy is to get log of something equal log of something and then set those equal. So I want to get one log on both sides. So this is log base 2 of x minus 5 over 7 equal log base 2 of 2. Now I've got log of something equal log of something. I can set those equal to each other. So I know that x minus 5 over 7 has to equal 2. Multiply both sides by 7. X minus 5 has to equal 14. Add 5 to both sides. X equals 19. So when you have logs on both sides, you want to get log of an expression equal log of an expression. Set the two expressions equal to each other. When you only have log on one side, you want to get log of an expression equal a number, convert to exponential. So here I've got the log base 4 using my quotient rule. So that's the log base 4 of 2x over 5 equals 1. Now let's convert to exponential. This means that 4 to the 1 equal 2x over 5. I multiply everything by 5. I get 20 equal 2x. Therefore, x equal 10. Okay? That should be it for the review.